I've started the recording. So good afternoon, everyone, and welcome to the USGCRP Observations Interagency Working Group, or OBSAWIGS, seminar series for 2024. My name is Anna Connor. I'm the coordinator for IWG, and I'm working alongside our co-chairs, Diane Stanitsky, Deputy Director of NOAA's Pacific Marine Environmental Lab, and Barry Lefter, Rotational Deputy Associate Director of Research at NASA. So just as an overview, today's seminar, Private Commercial GHG Measurement Activities, fits within a series entitled Becoming a Climate-Ready Nation, a focus on greenhouse gases. Many of the seminars in this series are co-sponsored by the Carbon Cycle Interagency Working Group, and we appreciate their partnership. This series highlights many of today's pressing climate topics related to greenhouse gases that can only be addressed using high-quality Earth observations and completed with the help of strong cross-agency partnerships. So this series is intended to highlight the influence of GHG observations on everything from the atmosphere, ocean, and land to the cryosphere and human health, all within the context of an integrated system with the goal to complete a global stocktake every 5 years. So I'm going to introduce Barry Leffer from NASA, who is one of our co-chairs. He coordinated today's seminar and will be serving as the facilitator. So Barry, I'll turn it over to you.
Thank you, Anna. And I want to thank our speakers. We're fortunate to have two leaders in the field of remote sensing of methane from space. And Riley Duren is the Chief Executive Officer of the nonprofit CarbonMapper. He previously spent 30 plus years at NASA JPL. 35 years at NASA, 27 at JPL, where he served as the Laboratory Fellow and Chief Systems Engineer in the lab's Earth Science and Technology Directorate, with a portfolio of satellite mission development, operations, research and analysis, and applied science, spanning the agency's Earth Systems Science enterprise. Additionally, he was Chief Engineer for NASA's Kepler mission, and since 2010, he has been the Principal Investigator on multiple research projects funded by federal and state agencies, focused on multi-scale greenhouse gas monitoring systems. In 2020, he founded CarbonMapper with a public good mission to deliver actionable and accessible methane and carbon dioxide emissions data in support of decision-making and mitigation. So go ahead, Riley.
That wasn't me, but if that's my cue to start.
Yes.
Okay. Well, thanks everybody for organizing, and I recognize a lot of names and faces here over the years. It's good to see a lot of you again. So what's the target? 15 minutes? Is that what you're looking for? Okay, so I'll just start with the blanket apology. I'm here in New York for Climate Week, and so most of my material is intended for NGOs and policymakers and philanthropists, and so this is not going to be a science-heavy talk, but hopefully it'll give you a sense of what we're trying to do. And as Barry said, this work really, to some extent, was incubated by and supported by over a decade, probably almost 2 decades of various federal research programs, in particular NASA, but also NIST and NOAA and the California Air Resources Board. So we've stood on the shoulders of giants in getting the system in place. So what I want to start with is introduce to you what CarbonMapper is, who we are, what we're doing. So CarbonMapper is both the name of the nonprofit organization that we founded in 2020, like Barry said, but it's also the name of a coalition. We call it the CarbonMapper Coalition, which is a public-private partnership assembled with the entities you see here on the graphic that include our commercial partner, Planet Labs, NASA JPL, State of California, and some key NGO and academia partners. And that coalition is really focused on us helping CarbonMapper, the NGO, meet its public good mission. And that is, we are designed as a team to make data available and interpret it for decision support. And that includes a comprehensive multi-sensor data platform. But what really motivated this program was helping to contribute to the growing ecosystem of methane and CO2 remote sensing systems and to fill some gaps, in particular focused on high emission point sources. So the animation you see here on the right is an artist concept of our constellation of satellites doing kind of the paint roller approach to mapping a region like the Permian Basin and pinpointing emissions at fine scale, in this case with the satellites down to 30-meter spatial resolution. We're in phase one currently, meaning we are funded by philanthropy to launch 2 satellites. We launched our first one called Tanager 1 on August 16th. We're working to deploy several more in the coming years. And our goal in phase two is to expand this constellation to increase the frequency and completeness of these systems, which I'll talk more about what some of those targets are. I do want to just, by introduction, I think Steve will probably have more to say about this, is that collectively, what we're working on is a system of systems, or a tiered observing strategy, where we need multiple satellites and other observational venues and sensor types to span the range of space and timescales, sensitivities, and use cases for methane and CO2 data. And this should not be a surprise to any of you in the federal space of the need for multiple platforms. I do want to highlight what I refer to as 2 general classes or types of monitoring for methane. I want to focus mainly on methane in this talk. What I call type 1 is aggregate scale accounting. So think of inventory, greenhouse gas inventories and quantification at the state of jurisdictions like states, countries, and so forth. Think national inventories. And type 2 is data that's focused more on providing localized mitigation guidance, like things like leak detection report on the ground at an individual facility, focus more on detection and attribution. And you can imagine they're observing systems that overlap and contribute to both, but most observing systems tend to be more focused on one than the other. And that kind of gets to the core of what we're trying to do at CarbonMapper. You're also, I'm sure, all aware that there have been, dramatic technological advances over the last few years, but there are some remaining gaps, and they have to do with completeness, timeliness, trust in the data, user awareness and ability to act on the data, and then finance. And that's something that I think we're collectively trying to confront as a community. And by the way, I'm in this presentation mode. I'm not able to see the chat comments. So if I'm not coming through, if somebody needs to tell me something, just holler.
Yeah, we'll help you out, Riley.
And then again, it will be good to get Steve's take on this, but just real quickly, the high level, this is the top question we get whenever we talk alongside MethaneSAT is like, what's MethaneSAT different than CarbonMapper? And my analogy is the 2 programs are designed to work in concert and complement each other. And the simplest way to boil this down for decision makers, CarbonMapper is really focused on facility level identification of high emission events to drive action. And while we contribute to quantification, that is really MethaneSAT's bailiwick about getting precise quantification, both of high emission sources and major regions. And we work closely together, both as NGOs and satellite teams. And we're really excited about having these 2 programs start to coordinate as soon as we finish our relative commissioning efforts. For CarbonMapper, we're using a technology referred to as imaging spectroscopy. This is visible to shortwave infrared imaging spectroscopy developed at NASA JPL over the last 3 decades. I'll go into some specs later, but basically we image and quantify point source methane and CO2 plumes at high resolution. And we also, in other bands, we can detect things like flare signatures. So we try to characterize what we're seeing in multiple dimensions. Want to emphasize that what we do is we're trying to be very focused on what part of the ecosystem we see of fluxes, and just to, again, for a policymaker, to make this a really simple comparison, an example of a point source versus an area source. If you look at an idealized landfill, there are lots of little emissions around the facility that could collectively contribute to a net diffuse area flux. We call that an area source. And then there might be one large high emitting source, like a leaking gas capture well or an unlit flare. And in this example, they could each contribute about the same, the area source and the point source. This is what we're trying to do, is focus on the point sources. Getting into the weeds a little bit more, if you look at a basin like the Permian Basin, and if you can make empirical measurements at some detection limit, in this case, we try to use a 90% probability of detection. If we survey a population like the Permian with a 90% detection limit of, say, 30 kilograms an hour for methane using aircraft, you have a pretty decent idea of what that population looks like. And then we could say, well, where is the peak of the distribution? And what we see with that kind of sensitivity is most of the emissions fall within 100 to 500 kilograms an hour for the point source component. And so this is part of what informs the design of our satellites. We've designed the CarbonMapper satellites to have a 90% probability detection of 100 kilograms an hour, with the idea of getting most of the methane iceberg for the point sources. Again, we're not talking about the diffuse area sources, which Steve will say more about in a moment. little bit more scientific. This is a paper published by Stanford a few months ago in Nature with using a million measurements from our aircraft and Inside M or Kairos Aerospace, looking at different basins. And the thing you should take away from this is number one is that there's significant variability in the distribution of emissions by basin, which is not surprising. But what I wanted to point out here is the devil's in the details on detection limits. And if you, the bottom line is for point sources, if you've got detection limits in the 1,000 kg/h range or up, and that is the case with most existing satellites, you're missing the bulk of the distribution. So I'm not trying to pick on EMIT, but these pink lines are the 90% detection limit for EMIT, which is about 1,000 kg/h. I think this slide may be skewed a little bit, and so you're missing most of a distribution. That's part of why we're going to lower detection limits. Other concept to put out there is data completeness. So if what you're trying to do is to maximize the amount of the net flux of a population of point sources you want to observe, it's important to consider not just detection limits, but the spatial coverage and the sample frequency, because many of these sources are variable and or intermittent. And so you can model populations based on what you posit the emission distribution is, but you can also model things like solar zenith angle, the albedo, wind speeds, and these things vary by region, and therefore you can start to map what the completeness of an observing system is as a function of the number of satellites, which gets to how much area and sample frequency you can deliver for a given detection limit. So these are just showing heat maps of completeness, red meaning I'm not seeing any emissions, green meaning I'm seeing 100% of a distribution, that is spatially resolved based on an inventory, in this case, the GFA fossil methane inventory at a 10-kilometer grid with different observing strategies. On the left, it's 2 satellites. On the right is 10 satellites. In addition to the heat map, you can see the one on the left is about a 50% completeness. The one on the right is about a 75% completeness. So this is kind of like running an Aussie, for those of you who like to run Aussies, for a point source imaging system. One thing that we get a lot of questions about is data, trust in the data and validation. And so there are kind of 2 methods that are used now in the point source world for evaluating satellite observations. One is control release experiments, like the one that Adam Brandt's team does at Stanford, where you release methane across a large dynamic range, both to probe the detection limit, precision and bias, and the quantification. And both CarbonMapper and others, including MethaneSAT, have participated in these studies before, and these are published in the open literature. The other thing you can do is use other aircraft using independent methods like mass balance in situ observations, completely different estimation algorithms over known emitters like landfills with simultaneous observations with remote sensing. And you can do plots like what you see on the right here of this paper by Dan Cusworth, published earlier this year. But this is a key to our element, to what we're talking about here, because this class of sensing is not compatible with the existing framework for validating satellite measurements like TCON for OCO and tropomi, because we're looking at very concentrated plumes, not diffuse fluxes, and the TCON network is not optimized for doing the latter. I will talk a little bit about our satellite here at the end, but before I do that, I want to remind you that a big part of what CarbonMapper does as an NGO is that we work really hard to translate this data into action. And so we have both a science team of people who are busy publishing, so what papers based on the data, but we also have a policy team who work closely with state, local, and federal governments, other NGOs, and civil society to try to understand what the needs are for the data and to translate it. And this is an area where we're probably going to see the most growth over the next year because there are severe capacity challenges on these fronts. Just a few examples of what we have done translating science into policy. One is, I mentioned the Evan Sherwin paper looking at oil and gas distributions across the U.S. and what it says about leakage rates and production. We published a paper recently in Science in concert with EPA colleagues to inform EPA landfill regulations. And we have some work that's coming on agriculture sector, looking at the efficacy of digesters on manure mitigation implications for concentrated animal feeding operations. And then lastly, on the NGO focus is that we make all of our methane and CO2 data public. We published over 17,000 methane plumes to date. This is largely today a combination of aircraft and EMIT observations, but we're using the same framework to process the new Tanager CarbonMapper satellite data And there's an API that allows people to rapidly access the data as well as bulk download capabilities. One thing I want to highlight is that we have done a lot of mitigation pilots working on about 300 cases now across the US, working with primarily state agencies, as well as oil and gas companies and landfill operators. And when we actively notify people, not just throw data onto the portal, but we actively reach out to an operator or regulator and we share data with them, we're finding in about 40 to 50% of the time, the operator regulator comes back and tells us that what we detected was previously unknown. And these are usually malfunctions or leaks. And then when they repair them, we can verify it with follow-up observations. So this animation just shows an example where we observed a methane plume from an oil well leaking repeatedly. We notified the operator. They went out the next day and fixed it. And then we report null detects. And this is really important. It's evidence of absence is as important as vice versa. And this is really important for a verification perspective to show that things work. And this is in particular, I think, important for EPA's super emitter program, which is geared to do this kind of notification. Okay, so I'll wrap up now with the latest cool stuff. So like I mentioned, we're using imaging spectrometer technology developed by JPL. A big part of this program was transferring that technology to our commercial partner Planet Labs so they can exercise agile aerospace to build a constellation of satellites referred to as the Tanagers collectively. We launched Tanager 1 a month ago from Vandenberg, and this is the first light image. It's one hyperspectral image cube over Karachi, Pakistan. This is 400 to 2500 nanometer spectral range. That's the layers you see in the end of the dimension of the page. 5 nanometer spectral sampling. Our spatial resolution will ultimately be 30 meters. We're currently in a high orbit, or a higher orbit for us. We're at 510 kilometers. We're over the next few months, we'll lower the orbit down to about 400 kilometers. That's our final operating orbit, which we maintain with solar electric propulsion. And that's key to us getting our detection limit and our highest resolution. Our revisit interval for a single satellite is 1 to 7 days for a quote isolated target. And those of you who've done a lot of mapping with tasking satellites will know that how frequently you can revisit depends on the density and size of the area you're mapping. So this number gets larger if you go to large regions. But the point here is to be able to bring these revisit intervals down to sub-daily ultimately as we build out the constellation. I haven't published, I'm not showing methane and CO2 plumes, but what I will say is that within 9 hours of that scene before we detected a methane plume and quantified it, and that's the reason we're able to move so fast is this pipeline we use for analyzing the data has been exercised for almost a decade now with aircraft and EMIT. So it really works out of the box. And stay tuned. Probably in a couple of weeks, we'll have a press release showing first light methane and CO2 detections around the world. These are some specs. I can make this available. The thing to take away from this is that our area coverage per satellite and our detection limit varies as a function of mode. So we have modes that can switch between larger area coverage and reduced sensitivity, or smaller area coverage and high sensitivity, including the ability to image over the ocean with glint mode observations. In fact, we're queuing up some of those, I think, tomorrow over the Gulf of Mexico. Tomorrow's probably not a good day. Hopefully the hurricanes cleared out, but we will be looking there. And then last slide, just to show you what our notional tasking deck is after we get out of commissioning. We plan to be out of commissioning by the end of this calendar year, start routine data delivery early 2025. But this just shows a map of different tasking areas around the world. These are different sectors. And to a large extent, we're looking at a lot of the same areas that MethaneSAT does. The major oil and gas production basins, cities, landfills, coal mines around the world. And the map on the left kind of shows you in a little bit more detail what individual tasking looks like. But I want to mention that this is not the full capacity. What I'm showing you is just the methane tasking deck, and we can image about 300,000 square kilometers per day per satellite. So over time, our flight rule is if we're over land and nobody's tasking us and we've got clear skies, we'll just leave the instrument on. And so over the course of the first year, we're hoping to get a full map of most of the land surfaces, including some high latitude stuff when we can get through the clouds. And I hope to show you in the first press release that we were already getting examples of looking in the gaps between clouds in the tropics and detecting methane sources. I've already got a half dozen cases of imaging stuff with like a 500-meter gap in the clouds. So we're super exciting to be able to turn a constellation loose on this. So with that, I'll stop and I'll hand it back to the organizers.
Thanks, Riley. We're going to save the questions until the end. So um, Riley was only about a minute over. And so we'll have Steve give his 15-minute presentation, and then we hope to have another 15 minutes for questions. I'm going to introduce Steve. Wofsy is the Abbott Lawrence Roach Professor of Atmospheric Environmental Chemistry in the John A. Paulson School of Engineering and Applied Sciences at Harvard University. His scientific work includes measurements and inverse modeling of fluxes of carbon dioxide and methane from ground-based, aircraft, and remote sensing measurements. He's the science lead for MethaneSAT, the satellite, and MethaneAir, the aircraft imaging spectrometers to measure methane emissions worldwide. And we just need Steve to go into presenter mode.
Yeah, I'm trying to do that, and got a little malfunction here. So just hold on a minute.
Sure, maybe you can drag your presentation up a little bit higher so that button.
I'm going to start again. Yeah, there we go. Okay, so now I should be able to do it if I can get back to Zoom. There we go. We got it?
That's working great. Thanks, Steve.
Okay, sorry for that little delay there.
No worries.
So thank you, Riley, for a really, really good introduction to the whole field. That's going to allow me to move a little quicker, get to questions. So MethaneSAT and MethaneAir are imaging spectrometers. They have quite high spectral and spatial resolution compared to other things that are out there. And we're going to talk about their mission and such in a little bit here. So MethaneSAT is really intended to bridge a gap between the global mappers like TROPOMI. TROPOMI has a 5 by 7 kilometer pixel, so meters there, but it's kilometers. Sorry, 5 by 7 kilometer pixels. It maps the whole world whenever it can see the ground and get a good image. That's very coarse pixel, though, for doing the type of regional and point source mapping that we need to do, as Riley expressed so well. Then there's the point source imagers, such as GHG and the beautiful CarbonMapper stuff that Riley just talked about. They have 30-meter pixels and a much narrower field of view, and are really excellent for finding point sources and quantifying them. But you don't really get the regional scale, you don't get the basin scale, you don't get the diffuse and area emissions. So MethaneSAT has a 200-kilometer wide swath, 100-meter by 400-meter pixel. It was launched into orbit on the 4th of March, and it's currently finishing its initial operating conditions, and we're expecting full operations in terms of data delivery at the beginning of 2025, about the same time as CarbonMapper. Let's talk about what we're trying to do here. So we really want to bend the curve and in other words, just try to reduce methane emissions to the environment. And our goal is to track the total emissions of methane to the atmosphere from oil and gas provinces globally, and to do it at the basin scale. So right in between those scales that can be done by the global mapper and the point source mappers that Riley talked about. We will be measuring in addition to getting the total emissions at the basin scale, we'll be giving information about the distribution over space and time in these places. And we want to use these to quantify the impacts and understand why emissions are happening. A little bit about the project structure. It's advanced science and engineering. It was developed more or less from scratch. It doesn't have that long uh, uh, history that Raleigh talked about in terms of NASA and JPL developments. We had outside science and science advisory committee and technical advisory committee to help us do this. As with CarbonMapper, the data will be distributed freely. All sorts of data products, including the emissions that I just talked about. We call that a level 4 product. And we'll also be releasing gridded maps and level 1 and 2 data, which are much lower level data as you move from raw to final product. And we have advocacy to outreach to industry, government, and the world, and it's funded by private philanthropy. Okay, this is just a quick shot of our data pipeline. Looks like anybody's data pipeline, except it's been developed on the Google Cloud, so it's a little different from what you would see in a NASA project. This has been exercised not quite as much over a long time as CarbonMapper, but it's been exercised over several years in the methane air, using the methane air data. Actually, I should mention we got support from NSF for some of this with methane air, so that's provided us with the data allowing us to really exercise this pipeline. This is a specification of the sensor. I'm not going to talk about it in order to save time, but it's a high resolution spectrometer, and it has these pixel sizes in the range of 25 meters for the aircraft and 100 by 400 meters for the satellite, a swath of 200 kilometers at nadir for the satellite and 5 kilometers for the aircraft. We're going to show some aircraft and some satellite data shortly. I'm going to skip over this. Okay, we have some first light images that we'd like to show you. These haven't actually been seen very much by anybody. They are posted on the MethaneSAT website. I'm going to show you some for this area in the Permian Basin. You can see the Texas-New Mexico border here. And this particular image that I'll show you was one of the early ones that we took. It's actually 400 kilometers wide by 200 because this was taken at a 45-degree look angle. So it's a targeted satellite with a fair amount of agility. And here it is. This is what it looks like. This hasn't been doctored at all. This is what it actually looks like. It's a little bit like like one of those Russian nesting dolls, you know. You can keep zooming in on this. I'll show you some zoomed in stuff. So these are 100 by 400 meter pixels on the right side and a little wider on the left side. Those the moth-eaten stuff here, those are cloud shadows that have been screened out with our with processes that we developed in using methane air. And you can see that the Permian has a lot of emissions at this particular time, very big ones. And we'll talk a little bit about those in a moment. Very exciting for us to get these first light images. These were dropped last week. They're in the public view for about a week. This one was taken on I believe the 22nd of May. I put a little round circle there. This is the Red Bluff Reservoir. I mentioned that because I want to show you a few others, and that reservoir appears prominently in the other pictures. You'll get a sense about what it looks like. So the goal of what we're trying to do is to give you a total emission for that area, as well as an emission map that looks like the ones I'm showing you here. These are not MethaneSAT emission maps. So level 4 data are not yet available for this. But our emission maps should hopefully look something like this. And you'll see we've done that for methane air already and gives you a good sense about what the capability is going to do. It also, this EIME inventory, for the particular view that we have here, totals about 275 tons per hour. And you can see the distribution there. This is the Delaware Basin. This is the Midland Basin, both in the Permian. And you have the EPA over here. It looks like a similar spatial distribution with about 1/3 the total emission. And we can definitely tell the difference between those. That will not be a problem at all. Now, if we just kind of zoom in and say, what do we actually see here? This is what our plumes look like. These are pretty big ones. This is, let me get rid of that. This is just three of those blotches that you saw on the slide there. We go through an automated program to isolate these plumes and weigh them and determine their emission rates. We have several different methods for doing that, and we combine them to get a reliable view. And in this particular case, we haven't tried to push down to the lowest limit. We don't know yet what our detection limit will be. This is just for the big ones. There were 11 of them, accounting for about over 60 tons per hour, just those 11 emission plumes. Now, what's interesting is we're very, very eager to be able to make these observations of emissions and their composition in terms of, which sources are important by over time. And you can see why, because here, I guess that other one was the one I just showed you was on September 11th of this year, so just a few weeks ago. Here's one from May on the left and June on the right, and they look really different because they are really different. And you're not actually seeing so many of those huge plumes. There's some big ones on the left, and there are basically no big ones on the right. That's a Friday afternoon, 3 p.m. view. I don't know whether that has anything to do with it, but as time goes on and we get more and more of these, we should really begin to understand this at the basin scale. That's something that's the unique thing that we can do for MethaneSAT, and that's what we plan to do. So that's really the bottom line here for us. Let me tell you a little bit about the data that we have from methane air. It gives you a real sense about what we're hoping to do with MethaneSAT on a global basis. We've flown methane air since 2021. As I mentioned, 2021, 2022, and 2024 flights of methane air supported by the National Science Foundation. This 2023 flights supported by MethaneSAT. And this is where we flew it in the Lear 35A. We have two of these, and I'll mention why that's important in a moment. But you can see we covered quite a lot of territory in 2023. And this is an image that we got from methane air. So methane air has a 5-kilometer swath, and so the way we make an image like this is to fly a Zamboni pattern like this, and move the pattern like that. And you can see in this particular day, August 26, 2021, it looks like that September image. There's just a lot of really big emissions going on out there. This area, of course, is much smaller than the one from the satellite. So this is 70 kilometers by 110 kilometers, still pretty good size, but not 100 by 400 kilometers. Riley talked about the importance of validation. This is a very big deal. I'm going to get back to that in a moment. As he mentioned, we've been able to do blind comparisons with controlled releases by the Stanford group. This is a really, really wonderful thing. So we do know the probability of detection for our aircraft satellite based on these measurements, and our modeling of the probability of detection as a continuous function of the wind speed, the total sunlight available, signal to noise ratio, all that stuff. So we have very, very good knowledge of that, and absolute confidence in our ability to do this. I just wanted to mention something about plumes. Riley was talking about the plumes that he's measuring, and for the most part, the point source mappers are going to focus on the part of the plume right near the source. But we can see the plumes as they go on out, and we can see them very reliably as they go on out. And you notice it gets dissected. The nature of this is different. This kind of is a stream, basically, a sort of tortuous stream. Then you get this kind of partially dissected mishmash of stuff. And then eventually um, what you see is that. So it merges into the general enhancement. And we can see all of that, and it gets to be very interesting because you begin to see that, there's a lot of large intermittent sources in some of these basins. Other basins don't have them, but the large intermittent sources give rise to this kind of lumpy stuff that you see out there. And that really helps us to learn about what the underlying morphology of these emissions actually is. So we have posted results from methane air, and I wanted to show you those. I'm going to bring that. Can you see the screen here, right?
Yep,
And
we sure can.
if I zoom in on this, this is all on Google Earth Engine, the Google Earth Engine app, and I can click on one of these and bring up the area emissions shown in the color here, and then the point source emissions. And there's a lot of them in this particular case. And if I click on that, it'll tell me about that particular point source. And we're going to be doing this for MethaneSAT. We have about, I can't remember how many of these we put up, a few dozen. We should be getting, when we're fully operational, somewhere between 10 and 20 of these per day from methane uh, MethaneSAT. Okay, I don't want to run out of time, so I'm going to move along here. This is my last really sort of real money slide. This shows how we do basin-wide total emissions and can compare them. This is just from the airplane. But you can see, this is the emission rates here. They're large for the Permian, and but actually the percentage of loss rate is fairly low compared to some of the others. Still quite high compared to the target of 0.25% that the companies have. But the big ones are actually not losing a very high fraction of the gas that they sell. Whereas some of these seem to be extraordinarily high, but that's because these are mostly producing oil. And so there's not much gas being produced, but a fair amount being emitted compared to what is actually being produced. Um, this is just a comparison to the to EPA inventories. You can see that the emissions on the basin scale are much higher than what's in the EPA inventories. And I'm now going to wrap it up. So basically, it shows that it was when it was launched, our routine data delivery for 2025. We are planning to deploy the 2 units of methane air to develop benchmark and validation data sets for inverse modeling. So that would mean our 2 units will be out essentially all day for several days in a row. In the case of one that we might do with the NASA team, we will have a LiDAR on board so we can actually look at night as well. And the idea here is to provide some kind of benchmark that's similar to what you would have for a controlled release for a point source. Nobody can release, known amounts over hundreds of thousands of square kilometers and then have you make a measurement and qualify it. But by repeatedly surveying a fairly large area, 70 by 100 kilometers, over and over again, day and night for several days running, we think we can lock down those emissions essentially by brute force, if you will, a mass balance experiment on steroids. So we are planning to do that. And so I am 2 minutes over, Barry. I'm sorry, but
No
I'm now done.
worries. Well, thank you, Steve and Riley. I'd love to open this up to the floor